plasma ball is a safe and engaging tool for studying high voltages in the electric field. A very large voltage is created by a Tesla coil-like circuit, and this creates a high electric field between the central electrode and the inner glass. Most physical science classes require that students have an understanding of plasma as the fourth state of matter. Glowing is a signature of most plasma, and so are free electric charges. On first inspection, you will notice that the plasma ball responds to your fingers. This is due to the polarization of your body, which is a decent conductor. As you approach the plasma ball, you become polarized by the electric field, and this attracts more of the free charges to you. Moving plasma can usually be controlled by magnetic fields, but this will not be visible for the plasma ball. It operates on a high-frequency alternating voltage, and because of this, the charges do not have time to get moving far or fast, so they will not get deflected. The very high voltages of the plasma ball can easily polarize a coin or piece of aluminum foil placed on top of it. By bringing your finger only a few millimeters above the penny, you will be able to elicit a spark from the top of the coin. This spark will not cause pain or electric shock, but will be hot, and if you hold your finger there long enough, it might begin to hurt. The tip of the finger will now show a few harmless burn marks that will rub off in a day. Use this sparking technique to explain how lightning forms due to the electric field ionizing the air. You can also touch a metal key or any conductor to the coin, and the spark will form between the two painlessly. Plasma threads are very hot, and they will rise due to their buoyancy in the other gases inside. For this reason, it is difficult to get a horizontal streamer to remain unbroken for more than a second, not unlike a Jacob's ladder. However, a vertical streamer at the top will be stabilized by the buoyancy. With practice, you should be able to get just a single vertical thread, but be cautious because the glass will heat up. The electric field can easily be investigated with a small neon bulb or light-emitting diode. Bring either of these near the plasma ball and they will light up. You can also study the globe's voltage directly by simply connecting a probe to one of the channels on an oscilloscope, and then you can probe the changing voltage spatially. Determine how the voltage decreases with radial distance by moving the probe in and out. For fun, or if you don't own an oscilloscope, you can also use an audio cable as a probe and listen to the frequencies on a pair of speakers. The human body can serve as an excellent antenna for picking up the signal, so be sure to touch the end of the cable's tip. Borrow a long fluorescent tube from your overhead lights or buy one at the hardware store and bring it near the plasma ball. You will notice that once a part of the mercury gas in the tube gets glowing, that it can stay glowing even as you extend it. There is essentially no limit to how far you can pull the tube. At certain distances, however, the tube will not glow. There is a minimum electric field required to ionize the mercury gas, and if the field is not strong enough, the tube will not light. It also works on the small household tubes. Demonstrate that the electric field can be diverted to a grounded shorter circuit if you grab part of the tube. This will reinforce the idea that lightning and other currents, perhaps later on, take the path of least resistance. Look straight at the plasma globe and place a finger as far to one side as possible. Analyze this with your diffraction grating and compare the spectrum to known inert noble gases. The vertical column will be ideal for analyzing its spectrum. Different globes use different gases and in different amounts, but they are almost always noble gases. Now you can put ionized neon tubes in the hands of eager students because your plasma ball ionizes them safely. No longer is a black box needed to confuse students as to what is happening. The plasma globe's strong electric field rips the electrons off their atoms, and unique colors are produced as electrons are reacquired by the various orbitals. Teaching about the emission spectrum of ionized gases can now become a hands-on activity. A plasma ball provides a safe source of high voltage that can allow you to investigate the properties of a cathode ray safely. Teacher and student alike can now safely and easily demonstrate magnetic deflection of electrons and relive the discoveries of J.J. Thomson thanks to the marvelous plasma globe. In conclusion, the plasma globe is an underutilized and relatively familiar piece of lab equipment. I strongly recommend that every physics teacher include one in his or her laboratory and use them to make studying electrostatics as hands-on as possible.